Hello, class. Excuse me. Yeah, a lot of lecturing done yesterday. A lot of lecturing done this morning. You know, this is only the second lecture out of 150 lectures that I have done. And then midway through the lecture, I realized that I had not prepared fully. And I made a mistake, and I thought, oh, okay, well, I'll fix that up. But then realized that, you know, really, you have to prepare for these lectures. You know, because sometimes you think to yourself, the source conversions, oh my God, you know, I know those like the back of my hand. I don't really have to put together a whole lecture. I've also got, you know, the lecture sort of here. And I know that it's got to work out there. So I'll just do it, you know, on the fly. I'll do it on the fly. And, you know, what you don't know, probably, is that it takes me about an hour and a half to 2 hours to prepare one of these 35 to 40-minute lectures so that, you know, I get the information across to you. And now that we're getting close to sort of the middle to the end of these lectures, and I've already finished all of the lectures for engineering mechanics, you know, you think to yourself, and of course, I want to expand on this idea as well, because in your job, when you get out and become an engineer, there's always a chance of becoming too comfortable with what you think is going on and how long it's going to take you to do things and everything else. Don't be that kind of engineer, right? Be the engineer that's always ahead of the game. Always try to stay ahead of everything. That's why I'm doing these lectures. That's why I'm trying to, you know, make it so that you guys learn 100% of what you would have learned if you were in front of me. Yes, I'm not an artist. I'm just going to try to fix those things up there. All right. So let me explain what I did. I came up with source conversion. I had this great problem that I had already done the source conversion one way on. And I was, you know, just during the lecture, I was going to do the source conversion the other way. So in other words, instead of replacing the voltage source with a current source, I was replacing a current source with a voltage source. And you know, I hadn't done the whole problem all before. I thought, well, it's just going to work out. And then when I did it for you guys, I did run into some problems, and I did look it up. I worked the problem out. It did work out right, but I had, you know, something that, you know, wasn't right in parallel. And so I thought, you know, I could, you know, I haven't even set up my timer yet, but I'm going to right now. I could have just like said, okay, well, you know, I mixed this. This should have been a positive. This should have been a negative. And, you know, but I didn't want to do that. I wanted to go back here. It took me a while, and I realized that there was a conceptual thing that I had missed, and I didn't want to just go back and do that. So let's start again. And what we're going to be doing is we're going to be converting series voltages. Let me draw the circuit that we would be converting. Let's say that I had a voltage source in series, right? Here's my voltage source, and I've got that in series with a resistor, right? Now, can I change that? Can I turn that voltage source in series with a resistor into a current source in parallel with the resistor? And the answer is yes. That would be the same R. We're just going to use Ohm's law, and we're going to make that conversion between the voltage and the current. And how would I do this? Let's just look at, let's say that this is a 10 ohm resistor. And this is a 12 volt power supply, right? V equals IR, and if V equals IR, then I equals V over R, doesn't it? That's right. So if I wanted to find the voltage source, the current source that I would put in parallel with that resistance of 10 ohms, because this is also going to be 10 ohms over here, right? Because we want those two resistors to be the same, and we want this equivalent source conversion to be the same too. So if I want a current source, I'm just going to go with V, 12 volts, divided by R, 10 ohms. So that would be 1.2 amps, wouldn't it? 1.2 amps. So if I replace 12 volts with 10 ohms in series, I could replace that with 1.2 amps in parallel with a 10 ohm resistor. Does everyone see how the source conversion works and why I was thinking to myself, well, this is this is a Sunday morning lecture. I'll have this thing done in a half hour. I don't even have to prepare for this. This is so easy. I've been doing this my whole life. And so you become cocky, right? Don't let that sneak in. Remember, always internalize all of the things that you're doing. So that's my thing. That's the source conversion. I could go either way with that, using Ohm's law, either V equals IR or I equals V over R. If I'm changing a voltage to a current, it would be that. If I'm changing a current to a voltage, it would be this. And so I wrote that down, and I actually did a simple problem up front. Now I'm going to do that one again. Where was that? There we go. Yeah. So the first example problem that I wanted to do, and this is a simple one, and this is what I really want to show you, this example problem now, because it shows you how much time and effort you can save by doing these transformations, right? And in fact, this is the first one I want to show you. I'm going to take that voltage source. This happens to be a 32 volt voltage source, and this is an 8 ohm resistor. Now, the current source that I've got here is a 6 amp current source, and then it's going to have 2 resistors here. One of them is a 24 ohm resistor, and the other one is a 14 ohm resistor. All right? So this is my circuit. And what I want to do first, just to do this, and and if I have, I want to point something else out. This is something that I probably should have pointed out a long time ago, but I think it's in your reading, and I'm sure that you realized it anyway. If I have voltage sources in series, right? Let's say I've got a voltage source there, and I've got another voltage source here, and they're in series, and this one is 32 volts, and this is 12 volts. Then, well, let's put some resistors in here too, make it a circuit. So if I have that, then I could really say that that is equivalent to a single voltage source, right, in parallel with that resistor. Or did I say parallel? I meant in series with that resistor. So I've just added these two together. So that's going to give me a 44 volt power supply. And then the resistor, I don't know, let's say that we've got a 330 ohm resistor. So that would be 330 ohm resistor like that. So these just add together. So power, voltage sources in series add together. Voltage sources in series add together. Current sources, right, in parallel add together, right? So let's write there. Excuse me, I did so many lectures yesterday. All right. Voltage sources in series add together. I'll just put an equal sign there, and I'll put an equal sign here, current. I can do this because I'm at the end of the book. Sources in parallel. Okay, so voltage sources in series add together, current sources in parallel add together. So that's what I've got here, and so what I want to do is I'm going to switch this out, right, for a current source. What I really want here is I want a current source in parallel now. I'm going to take that voltage source that's in series, and I'm going to I'm just redrawing the circuit now. I'm going to just add these things up. Now, this is about the easiest way to solve this problem. And I use the current divider rule to do it, won't I? Because I know that they add together. But what is that? I know this is 6 amps, but what's this one here? Well, let's see, 32 volts and 8 ohms. I equals V over R. 32 divided by 8 gives me 4 amps, doesn't it? This, by the way, is still my 8 ohm resistor. This is still my 24 ohm resistor, and this is still my 14 ohm resistor, right? So now I've got a new circuit. In fact, I can continue to simplify that circuit by saying, hey, you know, really, I have a 10 amp, right? Because I can add them together because they're in parallel. And then I have 3 resistors in parallel, don't I? The 14, the 24, and the 8. You know, can't I, because what I want to do is I want to find the current that is flowing through the 14 ohm resistor. Right? What is the current flowing through the 14 ohm resistor? So what I'd have to do is I have to take the current coming out of here, and I have to find out how much is going through each one. You know, can we combine these 2 resistors? 8 and a 24? Right? So really what I want to do is I want to have something like this. I want 10 amps coming out of here, and then I want 2 resistors so that I can just use my 2 resistor parallel current divider rule and figure out what that is. So we know this is going to be our 14 ohm resistor, but an 8 ohm and a 24 ohm, what does that give me if I combine those in parallel? Well, we have a rule, don't we? We have a rule that says R1 times R2 over R1 plus R2 is going to give me the equivalent resistance of 2 resistors in parallel, isn't it? Isn't that the rule that we learned a long time ago? So 8 times 24 divided by 32. Well, 8 times 24 is 192, right? 192 divided by 32. I hope I did that right. Yes, 8 times 24. I'm going to do that anyway. 8 times 24. That gives me 192, so I'm right. Divided by 32, and that gives me 6. So that would be 6 ohms there, right? So now what we've got is we've got 10 ohms, and it's broken down between a 6 ohm resistor and a 14 ohm resistor. So if I want to find out the current through that 14 ohm resistor, right, I would take the current that's coming into that resistor parallel network, and then I would multiply it by the inverse lever rule, right? 10 amps is coming in. We know more of it's going through the 6 than the 14. How much more? Well, 14/20ths more, right? Wait, no, 6/20ths more. Where's that? I kept thinking, what's going through the 6? Yeah, no. You know, what's going through the 14? And of course, what's going through the 14 would be 6 divided by 20. Sorry about that. 14 plus 6 is 20. What's going through the 14, that's what I was looking for. I don't know why I did the 6. So 6 times 10 is 60. Divided by 20 is 3 amps. Does everyone see how I did that and how easy it was? I'm going to drop a line down here, right? Because I want you to sort of see, well, this is the way that we did it to get the 3 amps. And what we did was we exchanged this part here for this part here. Let me get a colored pen so that I can, so we basically took this part right here and we replaced that part right there with this part right here, which is exactly the same as I've shown up here too. We can make that source conversion from the voltage source to the current source, and it made it a very straightforward problem, didn't it? Very easy now, because we could just combine the current sources. We have resistors in parallel. We can simplify those resistors in parallel. Voila, we get the answer. Now you're probably saying, well, Professor Grenquist, couldn't we also have done it the other way around? Couldn't we have taken the current source and replace the current source in the 24 ohm resistor with a voltage source? And the answer is yes. Yes, we can do that. Let's do that and see if we come out with the same answer, which I hope to God we do. And also if it's as easy as what happened here. I mean, this is such an easy problem, isn't it? Because we've got the current sources in parallel. We just switch it around. How long did that take us? About 5 minutes? That's right. Now, let's see if I did it the other way. Let's see if I kept that 32 volt power supply, right? So I've got my 32 volts now, and I've also got my 8 ohms in there. But now what I want to do is I'm going to replace that, right, with another power supply, aren't I? In parallel with it. You're probably saying, well, God, that would just make sense. I mean, if you've got a current source, everything else is in parallel. Wouldn't you, or a voltage source, wouldn't you replace the voltage source and the resistor in series with a current source and a resistor in parallel? That would just make sense when you're looking at that, because it's so much easier to work with current sources in parallel than it is to work with voltage sources in parallel. Absolutely. That's exactly what you would do. When you see a problem like this, the first thing you do is you say, okay, well, what are we doing here? If I replace this thing, I've got everything in parallel. If I replace this thing, I've now got 2 voltage sources in parallel. And this voltage source is 144 volts, right? Because this is 24 ohms. Now you're saying, well, how'd you get that 144 volts? Well, V equals IR. IR, 6 times 24 ohms, 6 amps times 24 ohms gives me 144 volts, right? So I've still got to keep the 24 ohms in series, in series with that. So that's what I've got. And then to finish my circuit out, all I've got is that 14, right, ohm resistor at the end. So going back to what I was saying is if you have a chance to put voltage sources in parallel, or you have a chance to put current sources in parallel, put current sources in parallel makes it a really easy problem. Did we have to do any mesh analysis or nodal analysis on this problem to solve it? No, we really didn't, did we? We just used the basic things that we learned in the very first part of this course. Pow, it's solved, because we knew enough as electrical engineers to switch out the voltage source in parallel with a current source in parallel and not do it the other way, which would make it really hard. Does everyone see how hard this is going to be, right? Because this is an 8 ohm resistor, 24 ohm resistor, that's a 24. So what we're going to have to do to solve this problem, to find out how much current now is going through that 14 ohm resistor, because that's what we wanted all the time, isn't it? And that's what we got down here. We know that it's 3 amps, and when we solve the problem this way, it should be 3 amps going through the 14 ohm resistor too, right? I mean, that makes sense. So let's solve this though. Now, it's not going to be as easy to solve as this one. right? Does everyone see what I've done, by the way? I just want to use my red pen here for a second. Let's go over to the original problem. If you look at the original problem, basically I've got a couple points here. I'm going to put a point here, point here, point here. Now I'm going to take that section, right? I'm going to take that section, I'm going to replace it now. So when you look at this up here, well, where's that attached to, right? Where's that attached to? That's attached to the bottom line. And so that's what I've got here. So I've replaced that with this. Does everyone see what I've done? I've just taken that out of there and I've replaced the 6 amps and parallel 24 ohm resistor now with a 140 volt voltage source with a 24 ohm resistor in series with it. So I've just redrawn this circuit here like I have. I've taken this out. I've put this in place. V equals IR. That's where I got the 144 volts. And so now I've got to analyze this circuit. And you're probably saying to yourself, hey, you know, that really lends itself to mesh analysis, doesn't it? That's right. Let's come up with 2 independent loop analysis equations so that we can figure out what the current is flowing through the 14 ohm resistor. So we've got 2 equations. Let's do them together. Here's the first loop, right? So I'll call that loop 1 and I'll call this loop 2. So I've got 32 volts, right? Minus 8 ohms times I1. Let's keep going around the circle. Now we're over here at the 24 ohm resistor, and that would be minus 24 ohms I1 minus I2, right? And then we're going opposite to the direction of the 144 volt voltage source, so it's going to be minus 144 volts, and all of that has to equal 0. Excuse me, I've already done one lecture today and I had to throw that one away. So my throat might not live through too many lectures today. But let's simplify this. So I've got 32 volts minus 144 volts. So that's going to be 112 minus 112 volts, right? Does everybody see that? So I've rationalized the voltages anyway. Let's do I. So I've got minus 8 ohms I minus 24 ohms I, which gives me minus 32 ohms times I1. Then I've got minus 24 ohms times minus I2. So that's going to be plus 24 ohms times I2. Everyone see that? Equals 0. There we go. Now, why don't we solve for I1 in terms of I2? Because you see this is a negative 32. Can't I just take this and throw it on the other side of the equation where I get positive 32 I1? And then divide both sides by 32, right? So I1 is going to be 112 volts divided by 32, so minus 112 divided by 32 gives me 3.5. So minus 3.5 volts. And then the 24 is just going to be 24 divided by 32 is 0.75. So it would be plus 0.75 I2. Let me just make sure that I've got that right. Yeah, 0.75 I2 minus 3.5 volts. Yep. In fact, I'll write it like this. Of course, you know it doesn't make any difference. I'm just going to, but I'll probably use this one as a substitution to throw the negative over there. Right, so I didn't have to use an extra sign. So that's I1 in terms of I2. And that was number one loop, right? That was number one loop analysis. And then number two loop, let's do that. Well, we're going up here. So it's 144 volts, positive, and then minus 24 ohms times I2 minus I1, and then minus 14 ohms times I2. And all of that has to equal 0. Why don't we substitute I1 in for that so that we can get the whole thing in terms of I2 with substitutional algebra? Should I simplify this a little bit first, though? Sure. So I've got 144 volts minus 24 I2 minus 14 I2. So I'll do this. Minus 24 minus 14 I2 plus 24 I1 equals 0. Now 24 minus 14 is going to give me 10, right? So I've got 144 minus 10 I2. Is that right? That's 24 I2, 24. That should be a plus. That should be 38, shouldn't it? Yeah, minus and minus. So adding those two together, and that's still going to give me the minus 38. What I want to find is, how 144 volts. I can use this spot. Minus 38 I2 plus 24 I1 has got to equal 0, right? So if I, haven't I? Yeah, that's right. Okay, so what I want to do is I want to substitute in for I1, 0.75 I2 minus 3.5 volts. So let's just do that. So 144 volts minus 38 I sub 2 plus 24 times 0.75 I2 minus 3.5 volts equals 0. So let's simplify this to solve for I2. I'm not going to do it all in one step. I'll do it in two steps so that I don't lose anybody. 144 volts minus 38 I2 plus, now, what is 3/4 of 24? Everybody knows that's 18, right? Divide 24 by 4, that's 6. 6 times 3 is 18. So that gives me 18 I sub 2. And then 24 times 3.5 is 84. So minus 84 volts equals 0. Let's just do this now. Minus 38 plus 18 gives me 20. Minus 20, I'll throw it on the other side of the equation. So 20 I sub 2 equals 144 volts minus 80 volts. I think everybody can see that that's 60 volts. And so I've got I2 equals 3 amps. What I want to point out here, and this is something that, yeah, great, yep, learned, use some more mesh analysis. That's fantastic. Always want to use more mesh analysis. Use the source conversions. Everything came out exactly right, whether I did it this way or did it this way. But which way was the easier? That's right. This way was much easier solving it. I didn't have to use mesh analysis. I didn't have voltage sources that are in parallel with each other, right? Current sources in parallel with each other add up. voltage sources in parallel with each other don't. So that's what I want to say is that we use these source conversions so that we can take something that's difficult, that would be much more difficult like this, and we can do it like this, right? Just using the fact that current sources add up in parallel. And resistors, we can work with the resistors easy enough. But it all comes out to the same thing, 3 amps, 3 amps, equivalent source conversions, equivalent source conversions. Some books call them conversions, some call them transformations, but it really comes down to, about the same thing either way. Source conversions, transformations. I've used up pretty much all of the paper now. I thought that I might get on to Thevenin's theorem, and I may even use this same example on Thevenin's theorem to show how I can, take this out of the equation and replace it with something. Although I have a very good example problem for Thevenin's coming up. I'm going to leave it there. This is a little shorter lecture because source conversions are, should be very straightforward and easy to use. The next one we're going to do is on Thevenin's theorem, and Thevenin's theorem is a very powerful theorem, especially when you're trying to rationalize and decrease the amount of resistors on either a printed circuit board or some type of IC package that you're putting together, right? And so that's why I want to talk about Thevenin's equivalency. And really that's what it is. We've got, you can take a very complicated circuit, and if you want to replace that whole circuit of resistors and wiring and everything else with one resistor and one power source, that's what Thevenin's theorem allows us to do. Another very powerful theorem that you'll use in both DC here and AC next semester. All right, see you at the next lecture.